Hey everyone, first I just want to say thank you to all who commented and watched my previous video where I tested ChatGPT o1 on Jackson electrodynamics. I think there was a lot of fruitful discussion happening in the comment section, and one of the recurring comments I got on that video was to possibly test ChatGPT o1 on problems that it had never seen before, problems that aren't perhaps floating on the internet. And so today I'm going to do just that, but first I need to go get some because I have a envelope of problems that my professor in grad school wrote out and gave us as assignments and has the answers to that I worked on. And so I want to get that and a few other books for my office. So if you want to go ahead and just skip to the testing part, go to this time. But if you want to watch the mini travel session while I go and get this stuff, here we go. So we're coming up onto my office area, which is at NASA Ames Research Center. I cannot be filming while I enter the base, so one last look before I get in, and I have to cut the video. Okay, so I got the envelope from my office. It honestly felt like I was stealing top secret documents, but honestly it's just my assignments from grad school from I think 2019, I think it was. These are the problem sets, which my professor just printed all of this stuff out, and he did not post it anywhere on the course page on the website. So these came from his brain. Maybe he did take some from books or whatever, but I'm pretty sure some of these are just his own construction, not taken from some known textbook. And not only do I have my answers, my solutions to the problems, he actually provided his own answers to the problems as well. And so I think this will be a great comparison. We'll have sort of two different human solutions to compare with the ChatGPT o1 solution. And I'm pretty excited to see if it can solve some of these problems. I'm not going to go through all of the problems because I don't want to just put his whole course up there for free. So I'm just going to select maybe 3 to 5 problems that I think are multi-step, ones that I think he came up with and are not taken from anywhere on the internet. And yeah, we'll see how ChatGPT o1 does with this. Okay, everyone, it is time to finally start testing ChatGPT o1 against the problems that my professor in grad school conceived of. Again, this is from my graduate astrophysics course in, I think I took it in 2018, 19, I can't remember exactly. But again, I don't believe verbatim these problems are on the internet. There might be similar problems that exist out there. But again, I'm pretty sure at least 2 of them were just from his own conception, problems 2 and 3. Problem 1, I think, is a fairly standard electromagnetism problem, I should say, but I really do want to see how it is going to perform. And as a bonus, I've thrown in another problem, not from this class, it's from another class I took. This is from the final exam from 2017, and it involves using Mathematica code. I'm going to give it this problem right here, which I believe I got a 95 on this exam, so I think more or less I got this problem correct, and we can see how o1 solution does against mine. So hopefully I'm covering as much of my bases as possible. Again, I will quickly just Google the first question. I'm pretty sure we'll find something like it just because it is a fairly standard question to ask someone in a class like this. So there'll probably be resources in its training data, but word for word, I don't think it exists. So I know I'm trying to cover as much as I can, but nevertheless, we're going to pop it in. We're going to see how it does, and we are going to assess its correctness or incorrectness. So continuing right where we left off from last time, here we go. All right, it's thinking. Let's take a look at its thought process. Considering polarization, confirming validity. The system confirms the question is acceptable and free from disallowed content and identifies the focus. What does that mean? Free from disallowed content? What do you mean? Okay. Okay, so we have to follow all those steps. Okay, so let's go ahead and take a look at how it did. I do also have my own answer right here, I believe. So let's, sorry, I just want to get the zoom. Okay, so it thought for 5 seconds this time, shocker. And it says here, to show that the same result is obtained for unpolarized light, we will assume the incident in wave is linearly polarized in an arbitrary direction in the xy plane, demonstrate that the orientation of the polarization in the xy plane does not affect the derivation of sigma t, conclude that sigma t is the same for unpolarized light by averaging over all possible polarization directions. I don't think you need to go through all of that, do you? I'm looking at my solution here, and I have my professor's solution like right here. And I don't think you actually need to do all that. That might be not the right way of going about it. But it starts with the same thing that I did. It starts with the equation of motion right there. So we kind of have the same idea. It's just that we've defined our electric fields to be different. I think just because I've set some angle here. I don't know what it did here. Did it just call it phi? Okay, so I think it just uses phi instead of theta, which is what I used. But okay, so far that's an appropriate way of going about it here. So the way that I did it is that you use Newton's laws of motion, so you can solve for what x and y are. Okay, so it's doing it in component form. I see what it's doing. So it uses the vector notation. Instead of me sort of separating out by components, it's actually doing it in the vector notation, which is totally fine. But I don't think you really need to do all of this. It's bringing out the delayed time here. I think this is a little bit overboard. I don't think you actually really needed to do this. Yeah, actually I don't think it's getting it, to be honest. Correcting the calculation. This is going way beyond that I think one needs to really do, because at least the way that I had conceived of it, you can just get the dipole moment, take two derivatives of that, and then, right? So, I mean, it says the square of the dipole's moment is independent of theta. Yeah, so this feels like it doesn't need to do all this. Does it get this answer? What is this answer here? Geez. Sigma t, oh boy. So it does get 8 pi over 3. Okay, it does get 8 pi over 3 r naught squared. Does it define what r naught squared is? Did it just say that r naught squared is all those constants? I think I'm losing the plot here. Not off to a great start so far. Oh wait, actually, yeah, okay. E squared over mc squared. That's, yeah, okay. Wait. Oh, okay, yeah, that's great. Okay, so it did get that. Okay. I don't know. I'm not taking a deep dive into this, but I think it went about it in a way more complex way than I would have gone about it, like getting the differential cross section, which, you know, this is kind of funny. Like, we're just on the first problem, and I'm already kind of like, I don't know about this. Wait a minute here. It says here, but they get this differential cross section here. This suggests that the scattering depends on the angle phi, which contradicts our expectation that the cross section should be independent of phi. So it actually did something that did not validate the answer. I think the way that at least I showed it was that you just have to show that you can get to this point where you essentially get the angle to have a cosine squared and a sine squared, and then you know that just makes it go away. So yeah, I don't think it got it actually. Okay, so I think I mean it got this in the end here because it did that integral. So I think it did get it, though it went about it in a way that I and even my professor here, like, I don't know, we both went about it in ways that were very different. And so, yeah, my professor actually did it the same way that I did it. Yeah, and so, okay, I don't think... Yeah, I don't think it did it exactly the same way, but it did reach the same conclusion in the end. This is the right expression for the Thomson cross section. And I know I need to move on to do the other problems. It's just that I'm actually kind of surprised by the approach it did here. It completely went against my expectations. The complexity of its approach, that it seemed like it did it wrong at first. And I'm trying to understand how it did it. Okay, so it averaged over the directions and then the incident polarizations. Huh. That's interesting. I don't know about the validity of this approach. I mean, it got the final Thomson cross scattering section at the end correct, but I don't know. I don't know if I want to give it a full 100% on this. I might give it like a 75 out of 100 or maybe an 80 out of 100, but I'm not giving it a full score. But who knows? Maybe I'm being too harsh on it, and maybe I should give it points for being creative and doing it in a way that I would not have done it or my professor would have done it. So I think that's all I'm going to have to be able to say about this, because I think we do need to move on. But I am surprised. It has surprised me with this approach, and I'm impressed that it got the final answer, even if it took a very roundabout way of getting there. Okay, now, so let's go ahead and pop in the next problem that I'm asking it to solve. So this is problem 2 now. I'm just going to go ahead, again, copy this, put into Google. Let's just make sure it's not like something that we know the galaxies. No, it's not the same problem. Okay, so quick Google search. I think people are actually using known Hubble constant, but in this problem, we're going to be just using the general little h as the parameter. So okay, let's go ahead. I'm going to give it the LaTeX. Should I give it the LaTeX or should I give it the... I'll give it the LaTeX. Hopefully it can translate this. If it doesn't, then you can blame me. But I think it should be able to understand that at the very least. So, okay, problem number 2, bombs away. Okay, that's thinking. Analyzing the problem. In fact, let me get my own answer out here. This is in problem set 3, I believe. So, got to get my answer out here somewhere. Looks like it's still working. I'm actually curious. How is it doing here? Establishing emissivity, calculating thermal Bremsstrahlung emissivity, working through the conversion. Crunching numbers. Okay, let's break down the temperature calculation. I'm multiplying, dividing large numbers, ensuring the exponents are tracked accurately. This helps me arrive at the temperature and its square root. Calculating electron density and working through the electron number density. Okay. So again, my answer to this problem, I believe this is problem 3. Yeah, so this is the way I solved this problem, and I believe I got a full mark. I got full credit on this problem. So we're looking for these kinds of answers. These kinds of answers. Everything boxed is the answer here. So let's see how it's going to do. Okay, all right. So first things first. A lot of numbers here. Can it actually do this? Don't feel too bad if you don't. Whoa, that's a lot. That's a lot. Okay. 2 times 10 to the minus 3. That looks very close. Uh-oh. Uh-oh. It looks like it got the right answer there. Wait, did it get the right units? Sorry, it's moving too fast. I guess I should just wait for it at the end. But that looked like it was correct. Oh boy. Oh boy. Summary. Okay, 2 times 10 to the minus 3 square root of h centimeters to the minus 3. That is correct. Oh my. That is correct. Mass of the gas. Did it get that right? Mass of the gas. 3 times 10 to the 13, h to the minus 2.5. That is that. That's that. Wow. That's correct. That is correct. Thermal energy of the plasma. What's the final answer? 1.38 times 10 to the 63, h to the minus 2.5. So I got 1.35 times. That's pretty much it. I mean, what did my professor get here, actually? Hang on here. I want to see. Is this problem set 3? Sorry, I have so many papers here. And if you can't tell, I'm a little bit flustered because I'm just like, whoa, this is incredible that it actually got it. I actually thought it would struggle with this one because it was it's a multi-step problem that involves numbers. What did my professor get? Did he get these numbers? I mean, it must be something comparable. Yeah, he got 3 times 10 to the 13. Yeah, 2 times 10. Okay. E-thermal. So my professor gets 1.5 times 10 to the 63, but I got 1.35. So yeah, he got for e-thermal 1.5. Oh my gosh. And then the cooling time, he gets ChatGPT o1 gets 4.37 times 10 to the 10 h to the minus. Yeah, that's pretty accurate. My professor gets 4.7, I think, for his numerical factor, but it did it flawlessly. Flawless. I mean, is its reasoning correct? I mean, I feel like it had to get correct reasoning to be able to do all of that correctly. Let's just take a look at its thought process. I don't want to dwell on it too much, but I do want to see how it approached it versus how I did, at least for the first part. So you do D is equal to V over H naught. Did I do that? Yep. Okay, so we got that. Physical size of the cluster. Okay, 1.05. Oh, wait, so... Oh, okay, so yeah, so we get this, R's, that, convert R's centimeters, volume of the cluster is like this and this. Just some numerical round-off errors, but more or less is doing what I was doing. Yeah. Yeah, so it's that. Oh my gosh. Ni, why did I do that? Is it just squared? Oh, okay, yeah, because we do Ni equals Nh equals Ne. Yep, okay. Yeah. Yeah, okay. I don't know how you argue against that. I don't know how you argue against that. I mean, yes, these are all problems that it may not exist in verbatim on the internet, but perhaps, problems like it exist and it could somehow extrapolate with all that. But even if it was, it's just, I don't know, it's like hurting my head to think about this. We're not even like halfway done with this, so I'm sorry. I know we need to move on, but I don't know what's the right word. Flabbergasted? Is that an appropriate word to use? But all right, we're going to move on to problem 3 now. Problem 3. Consider a spherical galaxy cluster in hydrostatic equilibrium. Suppose that pressure contributed by magnetic fields to the hot ICM is proportional to thermal pressure, this, and this. Okay, so again, the question is kind of multiple parts. If an observer neglects the magnetic pressure, will they overestimate or underestimate the gravitating mass? By how much? Okay. Let's go ahead and copy here. We now know they can solve it, even if it's in LaTeX form. So good to know. Bang and bang. Let's go. Let's see here. While it's thinking, I'm going to pull up my own answer to the problem, which I think is here. Okay, so yes. So it should underestimate the gravitating mass by a factor of 1 plus alpha. That's the correct answer. Again, this is my approach. You sum up all the different kinds of pressures here, use the equation of hydrostatic equilibrium. And I know we should just be looking at what it does. And oh my goodness. Oh my goodness. Wait a minute. Let's see. The true mass is larger by a factor of 1 plus alpha. Right. So yeah. So it got it correct. How long did it take? 16 seconds. So let's just see how it did it compared to me. Okay, so this is a problem that it probably, I mean, equation of hydrostatic equilibrium is a fairly standard thing, but okay, yep. So you do this, okay, comparing the true and observed mass from the observer's equation, substitute, let's see here. Yeah. That's correct. I think I forgot to post this in the Google really quickly. Let me just do that really quickly. I mean, I really doubt it matters. I mean, I'm fully impressed. But let me just put it out there just so perhaps, yeah, I don't think it's out here. At least not in exact words. But if people want, they can dig further than I can. But I don't think this is out there. So, okay, it got it. It got it. Amazing. So there's only one last hurdle for it to clear, and that's the mathematical problem. To be honest, after everything I've seen so far, and then yesterday or 2 days ago, wouldn't surprise me if it knocked this one out of the park. But it does involve coding, so I think we can at least hope that it won't get it. Let me just see here. Where's the problem? Oh, it's right here. Sorry, I didn't see that. But okay. Here is the final question, the mathematical problem, and then we're going to compare it to what I did. Okay. Go here. Put that in here. And all right. Here we go. Thinking. So, mapping out particle dynamics. Thinking about the equations of motion. Visualizing the trajectory. Okay, I'm laying out the Lorentz force equation. That's exactly how I started. Yep, you set up the equations of motion for A and B, determining the electric field, magnetic field, breaking down the motion, calculating the velocity components by analyzing the force per unit mass, including the cross product. So let's just see how I did it. I mean, this is my solution to the problem. You know, using Newton's laws, use the Lorentz force law, equation of motion looks something like this, and so on and so forth. So this is a little bit messy. It's going to be hard to like really compare side by side, but I will plot out its solution here. Breaking down the motion, problem analyzed, mapped out the solutions. Set of 4 first order ODEs. 4? 4? Wait a minute. Or B naught is equal to 5. Wait a minute. Why is B not equal to 5? Wait, how? Did they just give that to us? Sorry, I don't remember. Oh, yeah, it did. Okay, sorry, 5 is right there. Okay, so did the Lorentz force law. It looks good. Yep, that's what I would have done. Okay. Oh, I see. Okay, yeah, so this is the equation of motion. They didn't write it all out, but EX plus V YB. Oh, this is kind of messy to look at here, to be honest. Is equal to M times D position D2. Oh, yeah, so this is the magnetic field here. Oh, yeah, wait, it's V times BZ, right? Because that's, yeah, VY. Oh, boy. Is it missing a factor of R here, or am I crazy? Right, actually maybe that's just encompassed in the Lorentz force law. Yeah, okay. So far, I think it's, oh boy. Oh boy. Oh geez. Okay, so it create an animation of the motion. All right, so here are the two codes. Here are the two codes that it wrote. We're gonna see how it compares to what I wrote. So sorry, I'm scrolling a lot. I just want to see. Okay, so we're gonna run this. Whoa. Oh, I see. Oh, wow. I mean, okay, so it plotted it in the XY plane. I mean, it didn't do it like this. It didn't use parametric plot, but that... Did it do the same exact thing? Let me see. Let me try and look at it in a different light, like here. Does that look the same as that? That looks pretty similar. That looks pretty similar. I'm not going to go line by line, but that looks pretty good. We're going to make an animation of the motion, so this is my animation. I think it's kind of lame, but that's what I did for the answer. Okay, let's see what it did for the animation. And all right, I'm going to be really sad if it just like wipes the floor with my animation, which honestly probably will, but you know, after everything I've seen. But here we go. Oh, whoa, what? Oh, this is really hard to see. Okay, this is not the best because I think the plot range is a little bit too high. Let's make the plot range like negative 0.5, 0.5, negative 0.5, 0.5. Oh, geez. Okay, so yeah, I mean, it's better than my... It's kind of nice it has this little arrow thing. I think I actually made it a bit too... Oh, I think I made it way too big, actually. Sorry, guys. I forgot what the magnitude was on the magnetic field, so let's just try that. Maybe that's a bit better. Yeah. I mean, it could be a bit better. Maybe it could trace it out a bit, but
I think this would have been a passing grade. I mean, if I got a 95 for putting this together, I think this would have done better. So yeah, everyone. Okay, I think I think it's time to discuss what we just saw. So we just saw ChatGPT o1 basically answer, I want to say, 3 out of 4 questions flawlessly, more or less. The first one I was still a bit stumped on. I mean, I think it overall got the right answer, but it went in a very convoluted way around to get to it. But even with that first problem kind of giving me some pause, the next 3 problems, I can't, honestly, I want to say can't believe what I saw, but I just saw what I saw. And I'm trying to think of ways to explain, you know, how this is possible. I mean, to be fair, all of these problems are questions that have known answers, right? I mean, there are hundreds of millions of physics problems on the internet using Newton's laws, the Lorentz force law, those kinds of things. And so I'm sure there are questions that are very similar to the ones that were given to me, even if they were not word for word, that perhaps the o1 model was able to just pull from its training, database and sort of extrapolate its way to the right answer. But even if that is what it did, I mean, you can't just deny it did all that. I mean, I'm still trying to wrap my head, like, maybe some of these problems like weren't, maybe these are just some textbook problems that my professor pulled from. I don't know. I mean, I didn't ask him, but we used a textbook in that class that he didn't give us questions directly from the textbook, obviously, because he wrote them all up. He didn't just assign problems from the textbook. But I'm just trying to think of ways how it could do this. I mean, I think the next test I would like to give it would be to give it like a research problem that I've come across in my like dissertation work. I think that would be kind of cool because I have been thinking of like rewriting some code that I've been meaning to make neater and more shareable with people. And so maybe for the next video, if people are interested, I can try and get ChatGPT o1 to try and recreate the code that I wrote for my PhD dissertation, just giving it the instructions. And maybe I can also give it the code snippets that I have. But I'm very impressed. I cannot lie. I heard what people were saying in the previous videos, like, oh, it's Jackson is a famous textbook it's all the problems are out on the internet and the solutions are probably on some website forum and people have worked on them for years, and so that's why it knew that. I was like, fair enough. Let's go and just look for some problems that aren't as easily findable or just are not on the web whatsoever. And I did, and this is what was the result. So I want to keep my head on my shoulders and not freak out too much about this because I'm excited. Like I am like, wow, I am like genuinely impressed at how it did this because I remember solving these problems, right? Like I remember thinking through these problems, solving them, and feeling rewarded for doing so. And it just did some of those problems in seconds, right? Less than half a minute. So it it makes me in some ways kind of scared, sad, excited, all of the above. It's like a confluence of emotions that it's just raw right now. So I'm sorry if I'm not entirely coherent and it's kind of just me babbling. It's really an exciting time we're living in, and I'm looking forward for new models, and I'd love to test these new models like this. And if people have any more suggestions as to how I should test it, I'm more than willing to listen. This video was a whole response to people's suggestions, so that's that. But thank you all for sticking around to the end if you've stuck around this long, and I hope to see you in future videos on my channel.